All right, the topic for the day today is inverses of matrices. And we're going to learn how to find the inverse of a matrix so that we can use it to solve a system of equations. So, first thing we're going to do today is learn how to find the inverse of a matrix. And this is pretty easy as long as you know how to find the determinant, which we already learned how to do. So first of all, if you have two matrices, A and B, if A times B equals B times A, which in turn equals an identity matrix, then A and B are inverses. Now let's back up for a second. Do you remember when we were multiplying matrices and we said it depended what order you multiplied them because you would get a different answer depending on the order you multiply them. They're not commutative when you multiply them. Well, if you do get the same answer when you multiply them, and that answer is an identity matrix, and remember, this is an identity matrix. It has ones down the diagonal and the rest of the numbers are zero. Then A and B are inverses. So that's what we want to find today, is if we have a matrix, we want to figure out what matrix is its inverse. All right? The inverse of a matrix A is denoted as A to the power of -1. Now I'm just going to call this A inverse, all right, when I'm explaining. So here is an example of inverses. This matrix times this matrix, if you do the math with all the lovely fractions, you get this. Which means I could switch the order of these two matrices, multiply again, and I would still get this. Alright? These are inverses. Let me show you how to find the inverse of a matrix. Now first of all, you can only do this with square matrices. And those are matrices that have the same number of rows as they have columns. And we're only going to do 2 by 2 today, because we only learned how to find determinants for 2 by 2 matrices. So first of all, if A equals A, B, C, D, remember this order, it's going to be really important to you in a minute. And the determinant of A is not equal to 0, then A inverse equals 1 over the determinant of A times, and we're going to mix up the members a minute. We're going to take these two members and switch them. So not A and D, but D and A. With these two members, we're not going to switch them up, but we are going to change both of their signs. So -B and -C. Alright, that's how we're going to find the inverse of a matrix. Now, it says if the determinant of A is not 0. If the determinant of A equals 0, there is no inverse matrix. Okay? None. Right here. If determinant of A is 0, then A has no inverse. So first of all, find A inverse if A equals this. So the first thing we need to do is find the determinant. So let's move this up here. And the determinant of A equals 6 times 1 minus -3 times 2, which is 6 minus -6, which is actually 6 plus 6, which is 12. Alright? So now we can find A inverse. So A inverse equals 1 over 12 times. Alright, now remember, I'm going to go through mixing these up. You're going to take the 6 and the 1, switch their order. So the 1 goes here, the 6 goes here. With the 2 and the -3, you're not going to switch them. You're just going to change their sign. So this is a -2, this is a +3. And now we're going to multiply. And this is just scalar multiplication. So 1/12 times 1 is 1/12. 1/12 times -2 is -2/12, which is -1/6. 1/12 times 3, which is 3/12, which simplifies to 1/4. And 1/12 times 6, which is 6/12, which simplifies to 1/2. And there we have our inverse matrix. All right, so let's try this again. So we have a new example. First thing we want to do is find the determinant of A. So this is -9 times -3 minus 6 times 5. So this is 27 minus 30, which gives us -3. All right? So A inverse is -1/3 times, and this is the part where you got to make sure you keep track of what's moving where. The -9 and -3 switch positions. So -3 is here, -9 is here. The 6 and the 5 don't move, but the signs change. So this is -5 and -6. All right, now we're going to do our scalar multiplication. So -1/3 times -3 is 3/3, which is just 1. -1/3 times -5 is +5/3. -1/3 times -6 is +6/3, which is just 2. And -1/3 times -9 is 9/3, which is just 3. All right, let's go ahead and turn the page. Now, we're going to use inverses to do something here, and that is to solve a system of equations. So, what I'm going to start with is essentially sort of a proof. It's a method. I'm going to show you the process that we're going to use. You don't need to write anything down, but just follow through what we're doing. I've got a system of equations, and here it is. And instead of putting numbers here, all my coefficients are letters, like A, B, and C, and D. So I have AX plus BY equals E, and CX plus DY equals F. All right? And this is just so that I have a general system of equations. The way I write this as a matrix equation is like this. I'm going to take the A, B, C, and D, and they go in a matrix. The X and the Y, they're in their matrix. Now you can multiply these. They're set up for multiplication. And when you do that, you have A times X plus B times Y. Look at that. That's what it is. Then do the next row. C times X plus D times Y. That's this. That's where it comes from. And it equals E over F. All right? So let's do something for a minute. Let's talk about these with names. So let's take this ABCD matrix, and we're going to call it matrix A. And the XY matrix, and we're going to call it X. And then B is the E and the F. All right? And I'm starting out with this, which is A times X equals B. That's what I'm starting with. Now, let's assume that A has an inverse, and it's called A inverse. If I multiply both sides by A inverse, which is what I'm doing here, remember that A inverse times A give me an identity matrix, right? Identity matrix. All I did here was switch my grouping, and I can do that. All right? So this is an identity matrix. Now recall this. Any matrix times an identity matrix is itself. All right? So this just equals X, which happens to be XY. So all I have to do over here is multiply A inverse times B, and I'm going to get a matrix that tells me what X and Y are. That's the process I'm going to use. So let's go ahead and go through an example where we do this. All right, so first of all, let's write this as a matrix equation. So if I do that, it's going to look like this. 2, -3, 1, 4. Times xy equals 1, 6. That's how I would write this as a matrix equation. The next thing I'm going to do, let's call this whole thing here A. Let's find A inverse. So first of all, the determinant of A equals 2 times 4, minus 1 times -3, which is 8, minus -3, which is 8 plus 3, which is 11. All right, so here's what I've got. A inverse equals 1 over 11 times, and this is the part where I think people forget, you've got to change the order of your members. So the 2 and the 4 switch places. And then the -3 and the 1 stay where they are, but they change signs. So this becomes +3 and -1. And all I need to do is my scalar multiplication. 1/11 times 4 is 4/11. 1/11 times 3 is 3/11. 1/11 times -1 is -1/11. And 1/11 times 2 is 2/11. Now, what I'm going to do on both sides of this equation is I'm going to multiply by A inverse. When I do this and multiply A inverse times A, I get the identity matrix, and the identity matrix times xy equals xy. So on the left-hand side, I'm going to have xy. Now on the right-hand side, I'm going to have to do some multiplication. So let's put my 4/11, 3/11, -1/11, and 2/11 in a matrix, and then I've got 1 and 6. And they have to be in this order because they don't multiply in the other order. So now let's go ahead and do that multiplication. So remember, this row times this column. So I've got 4/11 times 6 plus 4/11 times 1 plus 3/11 times 6. That gives me 4/11 plus 18/11 equals 22/11 equals 2. All right? So, xy equals, here's the 2. You've just got to figure out what y is going to equal. So let's do this row times this column. -1/11 times 1 plus 2/11 times 6 equals -1/11 plus 12/11 equals 11/11 equals 1. And we're done. No decisions were made. This is purely a mechanical calculation. We never had to make a decision. All right, let's do another one. All right, so first of all, I'm going to start by writing this as a matrix equation. There we go. And remember, this right here, this is our A. So first thing we want to do, find our determinant of A, which is 1 times 5 minus 2 times 3, which is 5 minus 6, which is -1. So A inverse is -1 over 1 times, switch the 1 and the 5. So the 5 is here, the 1 is here. The 2 and the 3 just change signs. So this is -3, this is -2. And now we do our scalar multiplication, and this is going to give us -5, +3, +2, and -1. All right? So now, go back to our matrix equation and multiply both sides by A inverse. When we multiply by A inverse, this cancels because it multiplies into the identity matrix, which times xy leaves us with just xy. So what we have is xy equals A inverse times 2, 7. So let's go ahead and do our multiplication. Remember, this row times this column. So I've got -5 times 2 plus 3 times 7 is -10 plus 21 gives me 11. Do this row times this column is 2 times 2 plus -1 times 7 equals 4, minus 7 equals -3. So here's how we're going to write our solution. As matrices, xy equals 11, 3. And once you get the hang of the process, this is pretty easy, and you get over the fact that sometimes it's going to involve some fractions, but the fractions are always going to work out nicely because I'm not going to give you ones that end in ugly numbers. All right. Oops, here we go, -3. Let's go to the next one, and let's set this up as a matrix equation. So we've got -4, 3, 12, -9 times xy equals 7, 1. And this is A. So the first thing that we're going to do is find the determinant of A. So we've got -4 times -9 minus 3 times 12 gives us 36 minus 36 equals 0. Now, this is an issue for us because if we go to find the inverse, we're going to have to start with 1 over 0, which is not a number. All right? What this means for us is there is no inverse. There is no A inverse. What that tells us about this system is there is no unique solution. And by unique, they mean 1 point. All right? So here's what's going on. Either this is 2 parallel lines and they don't intersect at all, or these 2 equations are actually the same line. And so the solution would be all points on whatever line it is. We don't know which that is without further investigation. But for our purposes with matrices, we would simply say there's no unique solution. Don't say no solution, because there may be a solution. It may be the common line. There is no unique solution.